Hi everyone, we are Giacomo, Leonardo and Elisa from 3rd B, and we are here to tell you about a project that started in November 2022 while we are studying astronomy and physics. Using Legos, we had to build a working solar system with the aim of demonstrating how scientists discovered their first exoplanets. But what is an exoplanet?
First, we'll have to explain you what an exoplanet is. An exoplanet is any planet beyond our solar system that can orbit either or not a star. Those planets are called rogue planets or free-floating planets. And by studying the exoplanets' diameters and weights, we can understand their compositions. They can be rocky, gas-rich, ice, or dominated by water, iron, or carbon. As you can imagine, there are lots of exoplanets, and they come in a wide variety of sizes and compositions. However, astronomers have categorized them into 4 groups. Gas giant. They are the size of Saturn and Jupiter or larger, and they are composed mainly of gas. Neptunian. Planets composed mainly of gas, but of the size of Neptune or Uranus, with helium and hydrogen atmospheres. Super-Earth. A potentially rocky world larger than the Earth, and they might or might not have atmospheres. Finally, terrestrial, a rocky world outside our solar system. Some of them might have oceans, atmospheres, and organic compounds. First exoplanets were discovered around the 90s of the 20th century, and the first exoplanet was discovered in 1995, and it is called 51 Pegasi b. It orbits around the star 51 Pegasi, which is in the constellation of the Pegasus, at 48 light-years from the Earth. 51 Pegasi b has an orbital period of 4 terrestrial days. It has a surface temperature of 800 degrees Celsius and it weighs 140 times the Earth.
The aim of our project is to create a model of a planetary system to show how the exoplanets have been detected by measuring the variation of starlight intensity produced by the passage of a planet. We started out having in mind the idea of building a model of planetary system consisting of 2 planets rotating at different speeds. We had a motor, Lego pieces found at home, and some gears, both from the school, especially for this school project. In the design phase, we discovered a Lego piece created to reduce the speed of the motor. We inserted it into the model, but we saw that it was still going too fast to be able to take the measurements for either arm. At this point, we discovered that it was possible to decrease the speed of the model through structures of gears of various sizes. In fact, you can slow down the motion if it goes from a smaller gear to a larger gear. We mounted these structures, but we noticed that this time the arm was moving too slowly, and we could not get a correct measurement. So we decreased the size of the gear, and we finally able to get a middle ground between the 2 speeds we had previously, so that we could get the measurements right.
Now let's talk about how we took the measurements that scientists do in space, but with our model. We placed a phone on a pedestal and we used the Firefox application. This application allows us to use the light sensor on our smartphone to pick up the light intensity of the environment. At this point, every time the planets passed between the phone and the star, the smartphone registers a strong reduction of the light signal. This allows us to infer there is a planet around the star, and we know when the planet was passing because the light current was interrupted by the planet's shadow. And now Elisa is going to explain you more in detail this method, called the transit method, that gave astronomers the first evidence of exoplanets.
Transit is one of the easiest and most used methods to discover exoplanets. It is based on the astronomical event of the solar eclipse. If a planet is between its star and an observer, the passage of the planet blocks some of the star's light and the star gets dimmed. It's not a big change, but it can be a clue for astronomers to the presence of an exoplanet. The graphic you can see in this animation shows the so-called light curve. The straight line shows the normal level of light of the star, whereas the curve shows the drop in brightness. The graphic can also help astronomers determine the size and the mass of the exoplanet, as you can see from the first animation. The distance between the star and the planet, the orbital period, and how many planets orbit around the star, as you can see from the second animation.
Okay, now that we have understood how we can prove the existence of exoplanets, let's see how we interpret the data from our smartphone to see if exoplanets exist in this solar system. Looking at the graph, the green line indicates the time the sensor has been active. Instead, the blue line indicates the light intensity. Every time one of the two planets passed between the sensor, that will be the Earth, and the light-emitting star, a shadow was cast on it on the smartphone, and the result on the graph was a downward peak. The higher peak corresponds to the slower planet, and the lower peak to the faster one.